My name is Vladimir Travkin. I lead the team at Intel developing XeSS. XeSS is an AI-based capability for games that enables high-quality anti-aliasing combined with super resolution and brings significant FPS boost to those games. Today we will go through a quick XeSS introduction, followed by updates that XeSS 1.1 brings. We will also talk about best practices with XeSS integration and the upcoming XeSS Dataset Toolkit. These days, many game developers have moved away from rendering all the pixels equally in a frame in order to get better performance. There are a lot of different solutions to help with that and make better use of resources available in a modern GPU. AI-based upscaling and anti-aliasing, which we call super sampling, emerged as a great solution. It delivers a very good mix of performance and quality and is widely applicable across many game titles. XeSS is an AI-based super sampling technique which reconstructs a low-resolution, non-anti-aliased frame into a high-resolution, fully anti-aliased frame. And it does that at a fraction of the cost of high-resolution native rendering. This is a simplified pipeline diagram that breaks down a simple pipeline into elements such as render, post-processing, temporal anti-aliasing TAA, and UI. XeSS replaces TAA in the pipeline, and on top of anti-aliasing, it also adds super sampling. With XeSS integrated into the game, the rendering and initial post-processing steps are done in reduced resolution and require less time to finish, and this is where XeSS brings its savings. After XeSS does its anti-aliasing and super sampling part, the rest of the pipeline executes in the full resolution. This is a view on how XeSS works. It has inputs that are similar to TAA. Those inputs are the jittered low-resolution rendered frame, the jitter offset, and motion vectors, which are based on game geometry. All those are coming out of the traditional rendering pipeline and are fed into XeSS. Later in the presentation, we will get into more detail when it comes to the requirements on all those inputs. The lower resolution input frame is unjittered and upscaled to the full target resolution using a conventional upscale algorithm. Frame history is an internal input to XeSS that is hidden from the game developer. What we call history here is exactly the super sampled image that XeSS model has generated for the previous frame and stored it for internal use before post-processing is applied to that frame. Before the history frame is fed into XeSS model, that frame is warped using motion vectors we received from Game Engine to assure the history frame does match spatially with the current frame as accurately as possible, which is important to maintain high-quality reconstruction. So, the unjittered and pre-upscaled full-resolution input frame and the warped history frame are fed into the XeSS AI model. The AI model does its magic here, and the produced output frame is anti-aliased and super sampled to the selected output resolution. Then the XeSS output frame is fed back into the game rendering pipeline to apply the rest of post-processing. Now let's talk a little bit about the use of AI as a part of the upscaling technique. As you all know, there are different forms of upscaling, and not all of them leverage AI. Before explaining why we have decided to include AI in our approach, let's have a look at some of the challenges that all upscalers are facing. In this example, the upscaler is getting input frames with pronounced moire flicker. It is very difficult for the upscaler to reconstruct a sequence of temporally stable, anti-aliased, and upscaled frames from this type of input. This is a second example, and we can see flickering and shimmering in the water here. Why is that happening? Spatial temporal upscalers face a conflicting challenge. On one hand, they are leveraging history reuse, which is increasing the number of effective samples. At the same time, those upscalers are detecting and dropping stale samples, which is decreasing the number of effective samples. Reaching a proper trade-off is an inherently hard problem, which analytical upscale algorithms usually solve by manually crafted heuristics. Machine learning replaces those heuristics by an AI model, which we believe to be more robust and stable. When we started looking into an upscaling solution, we considered multiple options. We did some research, and the AI-based solution came up the most promising. This example actually represents an earlier version of the XeSS model. For this specific scene, we did a comparison with a newer version of the model, and we see greatly improved behavior on that type of content. Overall, AI-based approach shows a more robust behavior, and models can learn how to handle challenging game content. Although getting a robust model and high-quality visuals is important, ultimately we are striving to achieve better performance in demanding games, especially with ray tracing. As you can see, our Arc A-series GPUs combined with XeSS deliver great performance in demanding games. We can see more than 2x performance scaling with XeSS on some of those game titles. It is not a small uplift, and it can be a game changer for gaming PCs and for your games. This is a kind of performance uplift that should not be left on the table. To better understand where the performance uplift with XeSS is coming from, let's look at a visualization of what's happening inside a 4K rendered frame in a game title with and without XeSS. The dark blue is floating point, and the light blue is integer and other types of instructions. In traditional 4K, most of the time is spent on render and effects that precede TAA. And this is obviously where we have the biggest opportunity to optimize performance. When XeSS is turned on, the frame is rendered in 1080p, which significantly reduces the amount of time required to render the full frame. Only the post-processing effects are rendered in full 4K resolution. The XeSS pass is a bit more complex than TAA, but this extra cost is largely absorbed by the savings on the initial render pass. And our GPUs benefit from a second level of performance boost as XeSS is accelerated with XMX matrix instructions shown here in purple. We have probably not talked about XeSS for integrated GPUs enough. XeSS is actually compatible with integrated GPUs as well, and I want to spend more time on this chapter. When we created XeSS, we wanted to make sure it would be available on a broader set of GPUs, including Intel integrated GPUs and GPUs made by our competition. Speaking about integrated GPUs, those pose a number of challenges. They lack deep matrix hardware such as XMX, and their memory throughput is lower than with discrete GPUs. Also, XeSS input resolution is lower with integrated GPUs, typically 540p for gaming at 1080p, which makes it difficult for spatiotemporal upscalers to produce images without artifacts. Lastly, our research showed that we should keep the XeSS budget under 5 milliseconds to maximize benefit in the targeted FPS range of 30 to 60 FPS at 1080p. With those parameters in mind, we designed a smaller AI model. The good news is that while Intel integrated GPUs don't support XMX, they offer another form of acceleration for similar operation with DP4A instructions. We designed that smaller XeSS model to take advantage of DP4A and deliver a visual quality that is comparable to the higher XMX accelerated XeSS model. Of course, this is a smaller model, and it may not deal with the most complex situations as good as the larger XMX model does, but in most cases, it is doing a great job. In general, we have been quite pleased with how the smaller DP4A model performed in games, and it opens up millions of systems with integrated graphics to more demanding games. Let's look at performance we can achieve with XeSS on integrated GPUs with a recent 13th Gen Core i7 1370p based system. It is a 28-watt platform with 14 CPU cores and an Iris Xe graphics integrated GPU. As we can see, some of those games are not hitting the 30 FPS mark at native resolution, which can be considered as the minimum bar for the game to be playable. With XeSS, the performance level increases, and all these games illustrated here are moving into the playability territory. For your games, this can be a game changer. XeSS opens up your games and content to millions more PC platforms, including systems with integrated GPUs. Let's have a look at what that means with the demo of Arcadegeddon running on Iris Xe graphics. As you can see, Arcadegeddon runs significantly faster on this integrated GPU system with XeSS enabled, allowing for a better, more fluid gaming experience. Now let's have a look at an update coming to XeSS. As part of the XeSS software stack, we have created two models. One we called Advanced XeSS Upscaling Model and sized proportionally to XMX hardware capabilities, and the other one is a DP4A model for GPUs without XMX support. Those models are implemented in the form of high-performance kernels that run on GPUs. On this diagram, a DirectX 12 game is integrated with XeSS SDK, and it interacts with the XeSS through XeSS API. XeSS API is GPU vendor agnostic, and the API calls are automatically dispatched to the proper kernel backend. Currently, XeSS is supported only for DirectX 12. For Intel GPUs, there are two sets of kernels, one for XMX accelerated model and the other one for DP4A model. We did deeper, low-level optimizations for the Intel kernels, and we made sure to get the most out of XMX hardware on our GPUs and DP4A hardware on integrated GPUs. Alongside those Intel kernels, we built cross-vendor compatibility kernels that are based on Shader Model 6.4, which run on other vendors' GPUs and leverage DP4A acceleration. With the XeSS 1.1 update, we are introducing newer, better quality models. One of the focus areas when we built those models was to improve image quality and temporal stability. Along with the new models, we built new kernels to implement those models, and we've done extra efforts to optimize those kernels, so they are a bit faster than XeSS 1.0 implementation. We're also adding support for auto exposure capability that helps improve visual quality. Let's look in practice at the results of that work with XeSS 1.1 kernels. As you can see, the kernels are effectively a little faster, up to 20% faster on discrete GPUs and up to 9% faster on integrated GPUs. Kernel runtimes are dependent on output resolution, but not on input resolution, so execution times do not vary that much across XeSS quality modes. This performance improvement in XeSS kernels will help games get a small performance boost. For example, if you are targeting to run your game at 60 FPS, you now have up to half a millisecond extra time each frame for your rendering budget. When we started evaluating XeSS 1.1, we wanted to see how it handles some of the challenges we previously saw with XeSS 1.0, like flickering. For that, Crystal Dynamics was a great partner and allowed us to have a look at Shadow of the Tomb Raider with XeSS 1.1. The illustration we used earlier to show improvements we can achieve when the model learns to deal with difficult situations is a showcase of XeSS 1.1 in Shadow of the Tomb Raider. We can see that temporal stability has improved with XeSS 1.1 on the water and on some of the foliage. Now let's look at a few more examples of Shadow of the Tomb Raider with XeSS 1.1. Let's see if you can spot those temporal stability-related artifacts. Shadow of the Tomb Raider is a game with rich visuals, where XeSS 1.0 does a great job in general, but there are a few challenging flickering effects which we wanted to improve. To illustrate this better, let's zoom in. Stairs, as illustrated in the scene, can be subject to moire artifacts. XeSS 1.1 produces a cleaner render without moire. In this scene, the waterfall and fog are challenging elements to upscale. XeSS 1.1 is also doing a great job at eliminating flicker. The third example is probably the most challenging for all upscalers. The fences tend to suffer from moire and flicker, and XeSS 1.1 is doing a much better job. You may be wondering if these improvements will be generally applicable, and the answer is yes. XeSS 1.1 improves temporal stability across the board. And I should add two things. These new XeSS 1.1 models have not seen any content from Shadow of the Tomb Raider as part of the training process. And the examples we've just presented have been captured with the advanced XeSS upscaling model on an Intel Arc A770 GPU. The temporal stability improvements can be even more significant on the smaller XeSS model running on integrated GPUs and cross-vendor. Now let's look into a few more specific guidelines on how to integrate XeSS into your game. Let's get back to the rendering pipeline example. TAA is conceptually replaced with XeSS, as XeSS works with the inputs that are similar to TAA. So it is easy to replace your TAA or TAAU implementation with XeSS. The API behind XeSS provides a simple workflow. First of all, we define for ourselves the desired XeSS output resolution and XeSS quality preset. Those parameters are usually set by the end user in the game settings. Then, we will need to configure our game engine to render frames at XeSS input resolution, which is the lower than native resolution that corresponds to the chosen XeSS preset. For instance, if the output resolution is 1440p and XeSS preset is set to XeSS performance, then input resolution for XeSS would need to be 720p. In order to automatically determine the XeSS input resolution based on user-selected output resolution and XeSS quality preset, we query the input resolution from XeSS by using XeSS getInputResolution function, where we pass XeSS quality preset and output resolution. Then we create rendering pipelines and game engine resources, all in that XeSS input resolution. Then we initialize XeSS using XeSS D3D12 init function, and this is where we pass the quality preset and the output resolution to XeSS. For every frame, we record XeSS command buffer using XeSS D3D12 execute function and run it prior to game tone mapping. XeSS API automatically determines which model to run based on the underlying hardware. On Intel Arc GPUs, the XMX model, leveraging XMX hardware, will be selected to provide best image quality. The DP4A model will be used on Intel integrated graphics and on compatible NVIDIA and AMD GPUs. Auto exposure init flag is a new feature we added to XeSS 1.1 to automatically calculate exposure when the proper exposure value is not available from the game engine. XeSS AI models are sensitive to exposure correctness, so this new auto-exposure feature helps address ghosting and flicker artifacts in situations where exposure value is not available from the game engine. Auto-exposure comes with a small performance cost, so if correct exposure value is available from the game engine, it should be used directly with XeSS. XeSS supports 4 scaling factors, ranging from 1.3x to 2x upscale. XeSS Performance Mode is a 2x upscale and is recommended as a default option to get best performance boost from XeSS while maintaining visual quality that is comparable to native resolution rendering. Balanced XeSS mode is using a higher input resolution, and is a good choice when XeSS performance mode produces undesired visual artifacts. In those situations, XeSS balanced may yield better results than XeSS performance and help reduce the magnitude of those artifacts. XeSS quality and XeSS ultra quality modes deliver best image quality and temporal stability with XeSS, oftentimes better than native rendering. Those modes shift the trade-off between quality and performance towards quality and are especially useful with games where frame per second performance is less of a challenge and more emphasis is put on visual quality. If XeSS is already integrated into your game and you struggled with temporal artifacts like flicker and moire and had to resort to using a higher quality mode for XeSS, we encourage you to try XeSS 1.1 as you may see a lot more stable results. In our experiments, we are seeing that temporal stability with XeSS 1.1 is often better than with 1.0, allowing to drop the quality mode by at least one grade and get better performance without extra visual artifacts. In the rendering pipeline, placing XeSS at the right spot relative to post-processing is an important consideration that deals with trade-off between quality and performance. In general, we recommend integrating XeSS before post-processing or early in the post-processing stage for best image quality and temporal stability. However, in post-processing heavy titles, integrating XeSS after post-processing may provide the biggest performance gains. If XeSS is integrated in the middle of post-processing, try to avoid executing XeSS after depth of field, bloom, screen space fog, and screen space atmospherics, such as God rays and volumetric fog. These post-processing effects severely alter XeSS input image and make it harder for XeSS to properly reconstruct the frame. Let's do a little recap on XeSS inputs. Required inputs are low-resolution jitter input frame, jitter offset, and either high-resolution dilated motion vectors or low-resolution motion vectors accompanied with depth buffer. Exposure value is an important parameter to pass to XeSS either in the form of texture or a CPU variable. If exposure value is not available, then use auto-exposure function. Responsive mask is another optional input that is used to mark objects that do not come with correct motion vectors and cause visual artifacts with XeSS due to XeSS inability to properly reproject those objects during history buffer warp. A good example would be a semi-transparent particle that does not have proper depth value in the Z buffer. Now let's talk about important details to keep in mind when dealing with XeSS inputs. XeSS strives to maximize reconstruction quality, so it doesn't aggressively clamp color values from the history buffer, instead relying on the AI model to get the reconstructed image as close as possible to the unbiased estimate. The challenge with this approach to reconstruction is that it's inherently hard for XeSS to reconstruct the image from a limited number of high-variance noisy samples. That happens with strong specular reflections, especially with ray tracing on, high-frequency quickly changing moire texture patterns, as well as with ray-traced noisy shadows. We recommend using separate spatiotemporal denoising passes for such effects. The main input to XeSS is the low-resolution rendered RGB buffer, and we recommend passing HDR non-tone mapped input to XeSS to allow XeSS to apply the optimal tone mapping it was trained with. It's also important to pass correct exposure to avoid color overcompression during XeSS tone mapping due to too dark or too light input image. If the input to XeSS has been pre-exposed, then we recommend passing current exposure divided by pre-exposure. LDR input with XeSS is also supported, but is not recommended, as it may significantly decrease XeSS visual quality. As XeSS heavily relies on input that is subpixel jittered, let's go through a few important points to keep in mind when dealing with jitter. XeSS requires a subpixel jitter offset that is applied to every frame by the game engine, similar to how that is done with TAA. It is important that jitter sequence is long enough to establish good spatial coverage in the output resolution. Halton and blue noise sequences are good choices here. 32 is the bare minimum jitter sequence length required for the 2x upscale. We strongly recommend the length of 64 and higher for better moire convergence and flicker reduction. The rule of thumb is this: the more challenging the game content is, the longer jitter sequence is required to properly reconstruct the image. For best visual quality and stability, reflections as well as other complex effects should be unjittered and denoised before compositing with direct illumination. Some game engines, for example Unreal Engine, directly provide high-resolution dilated motion vectors to pass to XeSS. In case the game isn't able to provide high-resolution motion vectors, low-resolution motion vectors should be passed to XeSS along with depth buffer. XeSS will upscale and dilate these motion vectors to produce high-resolution motion vectors. If the game engine is able to provide high-resolution motion vectors, then those are preferred because they are more accurate. Motion vector accuracy directly impacts XeSS history warp accuracy, which in turn impacts XeSS visual quality aspects such as disocclusions, ghosting, and even flicker. XeSS supports both jittered and unjittered motion vectors as inputs. If you have integrated XeSS into your game and the output XeSS generates its shaking from frame to frame, then it is likely that there is an issue either with jitter values or with motion vectors, or even both. To debug this problem, first of all, try to invert jitter values or motion vectors and see if that resolves the problem. If not, then the motion vectors or jitter values themselves can be invalid. To troubleshoot the issue further, find a static scene and try setting scale factor to 0 for motion vectors. If shaking goes away, then the root cause of the issue is likely related to invalid motion vectors. Otherwise, the problem is with invalid jitter values. XeSS Inspector is a debugging tool that will come with future XeSS updates. XeSS Inspector makes it easy to troubleshoot and resolve XeSS integration issues, apply various overrides, dump XeSS inputs and outputs, and more. Let us know if you would like to get early access to the tool. Applying the Mipmap bias adjustment is important because XeSS needs texture details at the same or similar level as they are with native rendering. If you render in lower input resolution, then a lower resolution Mipmap will be selected by the game engine by default. Use the formula on this slide to calculate the proper Mipmap bias based on input resolution and output resolution. Log2 formula is a good initial approximation. If moire flicker is observed, then the general rule would be to increase Mipmap bias, which will help solve the moire problem, but may also make textures look less detailed. Conversely, if certain textures look too blurry with XeSS, then try decreasing the bias to make them appear sharper, but keep an eye for moire flicker artifacts. We encourage you to experiment with Mipmap bias to find the best trade-off value that delivers sharp enough textures free from moire flicker artifacts at different distances and viewing angles. For Unreal Engine, the XeSS plugin is available and greatly simplifies integration into Unreal Engine-based titles. With a simple copy-paste operation, XeSS is available from the editor and can be used seamlessly in the game. The plugin supports Unreal Engine 5 and Unreal Engine 4 versions that are newer than 4.26. For earlier versions of Unreal Engine, the code patch is available to enable the plugin. The XeSS Dataset Toolkit is a new upcoming capability that enables collecting and assembling a custom XeSS model training dataset from a particular game title, as well as retraining an XeSS model to improve its behavior on that title. The general XeSS model that is provided for integration into all game titles is trained with a dataset selected by Intel graphics experts. That training dataset allows XeSS model to generalize well and reconstruct a wide range of visuals, including elements the model has not seen during training. What happens if the model is presented with very unusual visual elements? Well, in general, the reconstruction is successful, but some specific visuals or scenes can remain a challenge and result in excessive flicker, moire, and ghosting artifacts. In that case, the solution to this problem is to include specific challenging visuals into the training data set and retrain the model for the next iteration of XeSS to improve its behavior on these types of visuals. We strive to simplify and accelerate this process for game developers with the upcoming Dataset Toolkit. XeSS Dataset Toolkit facilitates game-specific model improvements with two new components. First component is XeSS Dataset Extraction API, which integrates with the game engine and allows capturing training data. API calls must be put at the same spot in the game code where XeSS is invoked, typically prior to game post-processing effects. The API will make it easy to extract and save XeSS inputs, such as low-resolution HDR color, jitter offset, motion vectors, and depth buffer. It is important to note that the game engine needs to be able to freeze a particular frame and re-render it multiple times with different jitter offsets. This means that the engine needs to freeze time and suspend animations along with other dynamic effects for that particular frame to make that frame fully frozen and static. This is required to allow capturing multiple jittered, low-resolution frames that correspond to a single original high-resolution frame in the game. Each such sequence of jittered frames captured over a frozen static frame is then used by the dataset processing tool to reconstruct a high-resolution, high-SPP anti-aliased frame that serves as ground truth during XeSS model training. The second component of the XeSS Dataset Toolkit is the XeSS Dataset Processing Tool, which generates training ground truth reference in the form of high-resolution anti-aliased frames. Given those frames and all the corresponding data captured from the game, the Dataset Processing Tool creates a complete dataset to train XeSS. Provided with the game-derived dataset, Intel will retrain XeSS to improve its visual quality on that specific game title and will send back the updated model for integration into the game. The XeSS Dataset Toolkit will also come in the form of an Unreal Engine plugin for easy integration of the Dataset Extraction API. To recap what we talked about today, XeSS is Intel's high-quality, AI-based supersampling that works on Intel's discrete and integrated GPUs as well as on other vendors' GPUs. XeSS opens up games to millions more iGPU platforms. Follow XeSS integration best practices we talked about earlier to get the best visual quality and performance with XeSS in your game title. If your game already has XeSS 1.0 integrated, then we encourage you to check XeSS 1.1 out, which delivers significantly better temporal stability, especially on challenging game content. If you would like to improve XeSS image quality with your particular game title, the upcoming XeSS Dataset Toolkit will allow you to create a game-derived training dataset. XeSS 1.1 will be available later this month. Check github.com/intel/XeSS for the latest SDK. Thank you for listening, And don't hesitate to reach out to us if you have any questions about XeSS.